Hey, boy, I tell you, there's nothing like it when the internet goes out. The internet's been off all night, and boy, I got a lot of stuff done. No distractions at all. I guess the internet is a distraction because I couldn't, just browse around and do nothing. I got all these things done. I got so many things done. I got too much to show you in one video. But one of the things I did has to do with that. I haven't forgotten and I did say that I wanted to make this editor for the command box, right? Using a similar type of style of programming that you would for direct video access, and in the old days in DOS. My hard drive space has gone down. Anyway, so I've been working on this ASM file, and I finally got it going. It's not perfect, but it's more just a demonstration of the kind of thing and the way that these sorts of things build up. You start with, I suppose, what I could do is take away all these comments and let it compile. See, right now, because of my batch compile system is so slow, all this bit's already compiled, so I just work with this bit. It's quite quick. See. Oops. It's I have to do it that way, or else you have to wait forever. But what I could do maybe is have a second bar. This is a different position. 6, 9, 5, 15. Not that it matters, but I can't make it full screen anyway. Well, I could use my thing, but let's see. Let me just do a backup. And then I won't lose it. Well, look at all the things that changed since the last time. I haven't been here for a while. Actually, what would be easier? Put it in here. I call it direct, for direct screen, direct access to the video buffer, like DirectX in DOS. That was one way that you could access the screen. So the first thing I wanted to do was write a function called putS. You can sort of see, I just made the functions up as they were required, right? So that the way the ordering is it's not in a logical order, it's in the order that the various things came up. And it's not so easy to move things around with this. But I could reorganize it if I wanted to. And we'll just keep going. I don't know if there's going to be any conflict. It would be good to give it a once over. See, what happens is if you recall from the DOS stuff, what's this bit? Oh yeah. This is me testing the put s, which I'm not using anymore. So when that test, yeah. Well, I could put that code here. Before jumping off to 1,000. Put S here is defined as a C call, and its location 190. There should be plenty of room. That's certainly, well, no, that should be less than, is that less than 10? Let's see. Well, I don't even need this. I can make this 170. Just make absolutely certain. Or 160. Take away 2 lines. No, it's fine. It definitely fit. Okay. So we can walk through this. I think it looks better here. In this editor. Comment or something. I haven't really prepared this. Direct video drawing text mode, which is what I want to do, but make it a Win32 program. Same idea, but Win32 program. Okay, so now, actually this is good because I can, in the other box, I can draw pictures. And I can draw them with things like the rectangles and stuff. If I want, I'll use these characters. Alright. So now the idea is this. In memory, the video, the monitor, the screen, on computers has always been, since the beginning, one of the devices, unlike the keyboard, that uses this thing called, I think it's called DMA, Direct Memory. Is that what it's called? There's a name for it, something like DMA, and what it stands for is instead of using in and out, right, for the ports, the hardware, like a physical monitor, has like a memory on it, and that memory is mapped into the address space so that the processor can see it in just as regular memory. It's like virtual memory. It's like just like virtual memory. The hardware memory on the device, the video device, is mapped into the logical address space for where the programs and stuff are. Where programs, etc. And the processor can use it as if it were real memory. Like RAM. So the way that works is for a color monitor, let's start with CGA and then EGA and so on. This mode, this video mode with the colors, this has red, green, blue, background and foreground and brightness. We'll call that X or something. X RGB, X for brightness and red, green, and blue, which is 4 bits. And for both foreground and background and foreground. So that together makes 8 bits, right? So this here is the color attribute. You can define a color attribute for one of these cells, and all you have to do is just write a number there in memory. It's just as though it were regular old memory. And these, all these bits. Foreground and background. And then here is a character code. Another 8 bits. 1 byte. So 8 bits. So that makes up 2 bytes per character cell, and the whole thing you can think of as an array. This will make it look easier maybe. I won't draw the whole thing, don't worry. Just need a couple of these. So you can imagine there's that. Right, and that would be one line, and then there would be another line. Just like that. It's almost there. And just keep repeating this, and then you just write some value in here, and that turns on or off a color on the screen, and a character. So, for instance, whoops. Debug. Now, I can tell you the address. This starts. The address that's mapped, it doesn't matter what it is on the, what the monitor thinks it is, but the address is B800, segment B800, offset 0 is the top left corner. And depending on how much of the width and height, right, different modes and whatnot. So it's 2 bytes per cell, right? And let's say it's like this. This is 80 characters, and normally you would have either 25 or 50 lines. Okay, so you can imagine. Screen. Have a I have a magic clear screen that keeps me down here, so okay, I think we're okay this time. I had to try and I had to cut that a little bit off there because I don't want to be exactly on the bottom. If I'm on the bottom, then even if this is blank, it's still going to scroll. But we should be okay now. Yeah, I'm fine. I want it to be in the middle. Oh, well, we may not be okay. Okay, I'll just enter numbers in. Enter B800, 0. So it's the top left corner. First a character, 41 is the letter A, and then the attribute. It's, everything's always backwards. So this corresponds to the low byte of the word value that would go there. And the attribute, the normal attribute for what I do that for. That's what I have this batch file for, so it doesn't make those funny paths. So remember, it's XRGB, okay? Twice. So, so background, foreground. I think I had that backwards too. Background first. For white on black, this would be 0. And so 4 zeros. And for regular white, that's that, right? Which is 7. So letter A appears there. Now, the next character is at position 2, not 1, because it's 2 bytes per character. So put B there, and the attribute. Suppose we want, I don't know, you can get creative. Let's say we want, we could take the inverse of this one. Okay. So this would be the negative image, negative last, 70. Oops. So that's background white, foreground black. Next would be 4, 43 for C. Now let's add some color. Well, the way to make it colorful is to take away colors from white. How about black background and blue foreground? Right? So that's just one. So we can't really see it very well, but there is a blue C there, very dark. If we want to make it bright, I could repeat the C. It's an improved C. We can make it bright by changing this to a bright blue. Letter C, which is 9. So that's a bright foreground, background black, foreground blue. and so on. Just try and make one super colorful one before going. How about a bright background that's purple, that's red and blue, and a foreground which we could also make bright, and we could use the opposite of, if you negate all of the bits of this is purple or magenta, you get green. So that's bright purple background and bright green foreground, which is for 9A, right? A and no, 8. This is for 8, 9, A, B, C, D, D and A, D, A. Is that right? 8, 9, A, B, C, D. Okay, and then 8, A. Yes. So there you go. A very colorful, bright green foreground and bright purple background. So all there is to writing, to drawing on the screen is choosing the correct offset for your the coordinates you want. I can work it out. I suppose I want to put a letter down here. Work it out with the calculator. That's 50. Let's say that's 50 lines 5. Let's say line 40. 40 times 80 times 2 is 1900. If I wanted, the 40th line that starts at 1900 hex, and let's say at position column, well, at the middle is 40, so let's say 50. So 50, yeah. I'm doing the arithmetic in decimal, but the answer is in hex. So 1932. Whoops. We could do the same one, or similar. Let's make it a, I don't know, we'll do a mystery one, 52. It's still within somewhere within the alphabet, I think. Definitely. It's the 17th letter. How about, we want bright, so it's going to be more than 8. 9, bright blue, foreground, let's say bright purple, D. And that didn't work out, did it? Oh, that's right. I said 50. Yeah, that's not right. I should have multiplied this by 2. Should have been 1964. I always get messed up with 64, obviously. No, not 64. Well, I guess it's the same, isn't it? Multiplication by 2 is the same. That was an R, it turns out. So the next one's an S. And let's say A, E. There you go. So you see, you can draw anywhere on the screen simply by writing to the block of memory, which is a physical part of the monitor. Though it appears like regular memory to your program, even though this isn't mapping to those addresses in a real spot on this machine. I don't know where they map to. These aren't. This is not actually in text mode. It's a fake. This is using a font to simulate the text mode. In the end, even if you're using a font and having all these fancy graphics, there is a region of memory that belongs with the monitor, not with the processor. So it's on a different piece of hardware, and that memory is mapped into the logical address space of this computer that I'm using. Just as some other addresses sometimes map to the hard drive, because you can do that with newer operating systems. That's exactly what this is. It's a type of, I think it's called DMA, direct memory access, something like that. There was a special name for it, and the monitors use that particular method. Okay, I'll cut out the bit where I messed this part up. Character value. Now, typically the attributes are already all set to 7. 7 is black background and white foreground. If I dump, right, that means I'm dumping memory from here. I don't know if I'll catch this because it's going to scroll. But whatever. Yeah, missed it. It scrolled before we got to see it. Okay, well it's all filled with zeros. But if I keep doing this, eventually, now we're seeing them, right? You can see the 7s, the attribute, and the character. As these characters, even the blank ones, the spaces, have an attribute. It's not necessary. Like here, that's a space. They put the attribute in. Okay, so look at my program. Is that in the other one? So this is B800. Now my idea was this. I used to have a monochrome monitor, and that mapped at B0 into the B00 segment. So imagining I have a monochrome monitor, right? Or I have some memory mapped into that address. And then what I want to do is just like we do in Windows with the memDCs. I'm going to draw my screen into the monochrome B00 memory. And when I'm done drawing, I'm going to do a copy from the monochrome to here. And the reason I was doing it that way was so that it wouldn't scroll away, I guess. Well, and the other reason is if there happens to be dirty stuff, it just gets rid of it. If I blip the whole screen, then it's going to always be refreshed every time. Okay, so the first thing I wanted to do was clear the screen. Right? Well, actually, I didn't do that first, but let's look at that. That's not so difficult a function to think of, right? I decided that I would like to have this type of color, white on blue, which is 17 for the attribute. So I can look for a clear screen. Here it is. First thing I'm doing here is saving off the registers I'm going to be using. And now, using the new fact that the new discovery, without having to do any pushing or popping, I put the B00 segment value in AX, copy that into ES, because what I'm going to do is store word values using the repeated store Intel instruction for efficiency. And this is the value for if I want the order, I guess it should be flipped. That's correct, yeah. The way I was doing it was character then attribute. It's supposed to be flipped. In the register, it would have to be opposite direction. Okay. So character 20 and attribute background blue, foreground white, and the number I just worked out for the entire screen. An 80 by 25 works out to this is equal to 80, which is 50 hex, times 25, which is 19 hex, 7 times 2. No, not times 2. That's times 2 is how many bytes, but it's 2 bytes per character. And now I set destination index to 0, XOR, and this is how many I want to store. It goes into CX, and I use a repeated store. And if you recall the no double D's, double D, no double D. That's the handy trick to remember. If you're trying to figure out whether destination goes with ES or DS, okay, there's only one combination that agrees with the no double D rule. That is ES DI. So D means destination index. So this is either going to be a DS or an ES. Well, we can't be D, so it has to be ES. So there you go. DS DI would be a double D, and it's not a source; it's a destination. So therefore, we have the right to segment set to B00, and then we just do repeat store word, store string word, and that's it. Now that's written into my virtual buffer, right? In B00, you wouldn't see anything. So then, just like we do in Windows, the next step is to split the virtual buffer to the real screen. Find that. I have to do more than one on this. Oh dear. I use this one a lot. It's quite simple. Here, save off registers. The source is going to be the virtual buffer B00. So the source index, which has to go with DS, will be B's. So we need in DS, in this case, we need DS to be B00 and ES to be B800. And I actually used the computer to do the math. In this case, I multiplied AX 50 by CX25. I don't know why. I didn't realize till later on that you could you could pre-calculate that bit. Now, I forgot to do this CLI in the last one, didn't I? That doesn't hurt. Well, I put it in. It should fit. It's only one byte of instruction. I'll destroy everything. Where's the other one? What was it called? Here. This is it. Here. CLD. Alright. What did I have written there? So this should have a CLD. Clear direction flag. No, S set. Well, this is going to clear. Direction, I forget now. Okay, that should be increasing the steps here. Clear direction flag. Now, I didn't have CLI, I think. I just thought I might have. Oh god, I did. Okay. Because I just. CLI is clearly interrupt flag. That's a terrible thing. If it were a real machine, that would be a bad thing to do. That would have just hung the machine. Alright. I think we're okay. Alright, well, it should build from scratch now. I've saved it off. I've did it back up. So instead of C-Link, which now set up with my endpoint. Okay. It might take a while. This is why I clear all that stuff out. It hasn't even finished reading the file yet. Well, I can pause the recorder for this. Well, let's see how long it takes. Oh, there we go. It's starting. 17. It's not too bad. Oh, well, this is not used for anything. That's a waste. This thing grows like geometrically as you add the time taken. Grows geometrically as you add labels. My amazing batch compiler. It works, I should spend some time and just write a few helper programs to speed up this parsing. And then it'd actually be a decent tool. What I'd really like is a 32-bit assembler. Even that inline assembler, as great as it is, it's not as good as when you're doing it in real assembler, because you don't have all the directives, and you can't make variables, and you can't make structs and so on. As far as I know, there's a lot you can do with a real assembler that you can't do with other languages. You'd be surprised. I wonder what the progress is. it pretty much, you sit there and stare at nothing until it finishes. Oh, oh, okay, something's happening. Oh, darn it. An error. Jump one, so that's 1AA. Okay, comes after, just after a jump. These are lined up correctly. Oh, there should be there's a colon missing, I think. Alright, I know what that is. That's a different function, that's okay, a different function. The only times when they have to line up is if it's the same function. That's a different function. That's the whole thing. So you want that. Put S is after a jump. Oh, here it is. When you do it the very first time, then everything gets filled with CC. So there's no junk left over from previous build. We can still look at it in the other window. Direct. No, readme. So now you've seen clear screen, and it's very much like Windows. We have basically a memory buffer, a memDC, and the real BC. So to write a string out, I just arbitrarily decided that put 6 here. The current position would be here. The current position for writing will be stored at position 102. This happens to be 2 bytes, so this is position 102. And so it's starting out at x equals 0, y equals 6. And I had to put it at 6 so that it wouldn't scroll off the screen. While debugging. But here, the put s function I define as a C function, which takes a single argument, and it's a null terminated string. So at 104 is the null terminated string hello world. If I push that on the stack, C calling convention, so there's clean up here. In put S, this is how the problem sort of came up one after another. Okay, and enter the stack frame. I'm saving off these registers because they're going to be dirty. Now what I want to do is make sure that the top part of AX is 0. And now into BX goes the pointer value that was passed to this function, BP plus 4, if you recall. Plus is things passed in, minus is local variables. So that's this thing points to a pointer. That value would be 104 for that case. Now BX is something that can be indexed. It can be used as an index. 8086 LAN, only a few registers have that property. And here I'm checking to see if we hit a 0. If so, then we go to done. Otherwise, we're calling, break this problem down to printing out a single character. Again, C calling convention, taking a character in the low byte of AX. You can't push bytes on the stack. Here's a cleanup. And then I'm incrementing BX, and then jump to this label and that's a loop. I could have used a CX and used the loop instruction, but whatever. So here, this is the function for writing out one single character. C functions, enter stack frame, save some registers. Now this thing, get cursor pause, is a void function, and it returns well, in 16-bit land, an integer, really, an unsigned int, 16-bit value. And that value is x and y. As read from this buffer. Okay, now I could have just I didn't, maybe need to have. I could have just directly used the variable, but I thought it would be simpler if I added one more indirection for the cursor position, because maybe I don't know, I might save off the current state or something. Okay, so push that value on the stack, and now all this thing does is figure out the offset in video memory that corresponds to the XY value in this register. Now, if you just read in a word or D word or anything from a buffer into a register, you know that flips the values, right? In the register. But when you copy register the same thing back to memory again, it flips it back. So on the stack here, after pushing this AX, this function is going to see the bytes in the same order that they would have in their buffer. So calculate video offset. Again, it's a C function. Calculates the video offset in memory of one cell, byte values. We should probably, well, anyway. Now, I'm going to use these two registers, save them all, and my comment here just mentions that they get flipped again. So, in order to get it's X, Y, right? X would be lower in memory, and Y would be higher, just like in the buffer. All I've done is transfer that buffer onto the stack. 0 out dx, 0 out a high, into a low goes our character. So this is the y coordinate into a low, and then it's 50 characters per line. So I have now in AX I have the current line multiplied by 50. So I'm using a mul. Now add to so I take the y value and multiply by the number of characters per line. So I'm at least that far out in terms of slots. Then add the x coordinate, just as you would normally do. And there's one extra thing you've got to be careful. If there's a carry in this add, right, this is a byte add, then add that carry, increment a high by 1. Just regular addition. If there's a carry, you carry it over. Now this is a multiplication by 2, because it's word offset and then one character is 2 bytes, and then we're done. The return values in AX. We store the registers, return the stack frame, and return. And I think I'm going to have to stop here and resume next time. See if it fills. Okay, that's fine. That one's up. These have to line up to the same function, and they do. No collision, no. This is less than that. We're fine. That didn't line up correctly. This should be one. Gosh darn it! I can throw a no off in here. 217. Just remember. This is a new function, so okay. 217. Remember 217. That's a function. It's a full function. Inclusion. Let's see. Full function. No collision. Function. No collision. That's okay. It's a new function. Oh, I'm missing something. I have to add. I remember where it goes. Okay, that's fine. Ooh, oh, that's okay. Not a close call. That's good. That's fine. That is fine. Now we're at 1,000, and that should be okay. And you always get int 3s in between, so I'm going to put a no there. And the thing that I'm missing is the get function. It's supposed to go at 2f0. I should type it in. Okay. That's all there is to it, right? So get 2f0, which follows print car. Print. Oh. I can do it. I don't have to read the file. So I can just remember the address. 2f0. I forgot what it said. Two F0, right? understand what first. Okay. 800 int 16 10. Now it should work, as it turns out. Jump to 160. Now this one, that's the clear screen. If I run this, it should clear the screen. And it did, through the blue box. Now this is the printing of a string. So if I proceed over it, there's still a long way to go in following the code, right? We cleared the screen, and now we haven't even got to set cursor pause yet. Well, it's not that much. We calculate the address and find where the thing goes. And put the character in there. But anyway, I'm just going to run over it. There it is. Hello world. Okay. Now, why this? Oh, okay. That's because of the cursor got. I'm using this blinking cursor for the program, and so it ended up exactly where Hello World was printed at. Okay, AX, where are we? I'm just going to say go. So this is the program. So we have carriage return. So you see I can do all these things. Notice that nothing happened there because this thing doesn't, there's no backspace. This thing is doing direct screen write. This hello world is already in its screen buffer, in its virtual buffer. So it thinks that those characters should, every time I'm typing a letter, it's copying the full box, right? So that's why the other stuff that wasn't in B02 didn't say should be written because they virtual. Oops. But I just have to do backspace. No, I don't know if I have this exactly correct with the scrolling. I haven't checked the endpoint. No, it didn't work. But yeah, it's not properly clearing the bottom line in that case. But I think I can fix it. Now, since this is, I was trying to print out arrows. Since this is a direct screen write, then I can move the cursor around and I can draw boxes and whatever, right? In this mode, I'm not using standard I/O, right? This isn't writing to a file, this is writing directly to the screen. And so that's how people used to make things like edit, the program edit. And so this is an example of using direct screen writing. It took a long time to explain just that little bit. And there's a whole bunch of other things I did last night. I guess I'm a lot slower at explaining than doing. Anyway, I hope you enjoyed that little trip into the past. And look, somehow I lost another Where's my memory going? Oh, right, recording. Okay, well, see you next time.